Hello and welcome to Cup of Cosmology, the place for all your questions about the universe. My name is Deanna Hooper and I'm a postdoctoral researcher currently at the Helsinki Institute of Physics over in Helsinki, as the name implies, in Finland. And yeah, I'm a cosmologist, so that means that I study the universe, the cool stuff happening inside the universe, how things evolve, how things interact. And it's a really, really cool topic. I love studying cosmology. I love being a scientist in general, despite the many ups and downs. It is still a fun job. And I love chatting to people about all of the cool things I get to research. It's still mind blowing to me that I get paid to study random stuff happening inside the universe. It's such a cool job, despite everything. It's a good job. So welcome back to any of the regulars. Welcome to any first time viewers. I see we have a couple of the regulars coming in already, and David Howden, David Dunn. Great to see you all, as always. Great to have you here every week. I know some of you are here like every single week for the last 8 years now, and I'm still amazed that you all keep coming back week after week. Haven't got bored of me yet. Hey, Ben, Scott, great to see you as well. Another couple of regulars coming in. So if you're a first-time viewer, please do like, even if you're not a first-time viewer, please do like, subscribe, leave a comment. Subscribe if you're a first-time viewer and haven't subscribed yet. You know how YouTube works. Press all the buttons, make stuff happen. It really does help boost engagement. And given that I'm basically only using YouTube these days and the streams are no longer active on Twitter, or at least they're still there, but I do appreciate everyone who tries to boost the streams a bit to get more audience in, because the more people I have, the more questions, and then the more fun topics we talk about. Hey, Barth, great to see you here as well, as always. Really great to see all of the regulars coming in. So yeah, I'm a theoretical physicist. I study the universe, and the purpose of these streams is that you can ask me anything you want. So this means I don't have a topic prepared today because I have a lot of chaos going on with a lot of things. So that means that this is an interactive ask me anything. You decide the direction of the stream based on your questions. You can ask me basically anything you want about physics, about cosmology, about life as a postdoc, about grant applications. Maybe don't ask me about that if you want to keep me in a good mood. You can pretty much ask me anything and I will do my best to try to answer. If you don't have specific questions, then I get to talk to you about some of my favorite topics, which might include, for an example, dark matter and why we believe dark matter exists, or the cosmic microwave background radiation, the oldest light in the universe, less than 4 minutes today. This is another one of my favorite topics, or gravitational waves. Basically, ask me whatever you want, and I will try my best to answer it. So, hey, Paul, great to see you as well. Always nice to have you come in as well. I'm sure you're coming with tough questions. You people always have tough questions at me. And it's always nice. On the topic of tough questions, last week, someone here asked me, why doesn't dark matter interact electromagnetically? Like, what is the physical process that is preventing dark matter from interacting electromagnetically? So dark matter is this type of matter that exists in the universe that interacts gravitationally but doesn't appear to interact electromagnetically. We know that it's there based on how it gravitationally affects everything else, but we haven't been able to see it because it doesn't interact electromagnetically. Some people here asked me last week, why doesn't it interact electromagnetically? And I gave a hand wavy answer, like, it doesn't. And then I actually asked my colleagues about this. Hey, James, great to see you as always. So on Monday, I actually made a note of this last Sunday, and on Monday I mentioned this to my colleagues. And the general consensus was dark matter doesn't interact electromagnetically because if it did, it wouldn't be dark matter. So yeah, that was the answer. So it's about as hand wavy as the answer I gave last week. And now it's even more hand wavy, but now it's backed up by other scientists. So now it's like a peer-reviewed answer. So yeah, the general consensus was dark matter doesn't interact with light because if it did, it wouldn't be dark matter, it would be something else. It's like by definition, dark matter doesn't interact. So if we find something that does interact with electromagnetic force, then it's not dark matter. So that was general, and I was like, but what is the physical mechanism? And the general consensus in the office was like, well, it just doesn't. So my hand wavy answer last week is apparently as good as we're going to get in terms of hand wavy answers for why dark matter does not interact electromagnetically. It just doesn't. It's a general answer here. But I actually did make a note of that, and I did ask. So I do sometimes remember to go back to my list of questions and follow up on them. Not often, but occasionally I do. So Scott, you say you have a question about orbits in relation to planets and moons and stars, but it's too long to type out here. Yeah, you can absolutely email me with that. As always, you're all welcome to email me. The email address is contact@cupofcosmology.com. There's another one as well that I can never remember. Right, yes, there is also cupofcosmology@gmail.com. They both go to the same place. But contact@cupofcosmology.com. You can email me. I don't generally answer questions in my inbox too much because otherwise that would be a full-time job. But if it's one of the regulars and I know you, I've known you for years and you often message me on Twitter, feel free to send me an email as well. Contact@cupofcosmology.com. You can also just go to the Cup of Cosmology webpage and click the little email button on the top right-hand corner and send me an email there. Those I do check daily. So that's actually the easiest way to get hold of me is via email always. There was a nice question. For some reason, Restream is cutting off and only showing me the bottommost comments, which is kind of annoying, but at least I can see the latest comment. It keeps glitching slightly. Since most stuff is dark matter, not interacting is normal. So the question should be, why does light matter interact with stuff? Yes, I guess because otherwise we wouldn't see it and we wouldn't be having this conversation. So by construction, visible matter must be visible and therefore it must interact electromagnetically. Another hand-wavy answer for you there. Okay, so there was a nice question by David Howden here about something that happened in my week. So I mentioned on Mastodon earlier this week that I might have solved a long-running problem in one of my projects. What was it? Thank you for that question, David. That is a very nice question. So a lot of what we do in my projects and in my work in general, a lot of what I do is coding, right? We try to get the computer to do physics for us because what we want to do is very complicated and can't be done by hand. For an example, if we want to ask the question of what model of cosmology can explain the cosmic microwave background radiation best, like this guy up here, in case you've forgotten what it looks like, what model can explain this best? The way to do this is you run 1,000 or 1,000,000 different models. For each of these models, you calculate what the CMB would look like, and then you compare this to the actual observations. You do this 1,000,000 times, 1,000,000,000 times, and then you find which of your comparisons had the best match. This is just a statistical test that you do of, okay, if I play about and change all of my underlying physics. No, you missed a CMB. This was its second appearance. It actually appeared 3 minutes into the stream already. This was CMB number 2 today. You missed the first one. So yeah, blink and you miss it kind of. CMB has already appeared twice today. So yeah, we want to know which model fits the CMB best or any other data. We run this 1,000,000,000 times, 1,000,000,000 different realizations of the CMB, and then we compare the statistical properties of each to see which one matches the data. So one of my ongoing projects, we are doing this with mock LISA data. So LISA is a future space-based gravitational wave mission that is, as the name implies, this description implies, is looking for gravitational waves. And what we do is we create mock data. So this is because we don't have real data yet because it hasn't launched yet. So we make fake data that is as realistic as we can get it. And this data is like, what would a potential data set from LISA look like in the future? And then we try to see what we can find in the data. Now, of course, here we're kind of cheating because we put in a model and then try to find it, right? So now, instead of having some underlying model in the universe, we've put in a model and then we see, okay, can we actually recover this? Can we find it? Well, we find this is the best fit. We know we should because we put it there. So then the idea is you run 1,000,000 different tests on this mock LISA data to see if the best fit is indeed the model that you put in, and it should be. If it's not, then... So the question we're trying to ask is, will we actually be able to find it? Because the data is going to be very messy. There's going to be a lot of stuff happening. We need to take into account things like the way LISA is orbiting around the Earth and so on, or the way it's chasing the Earth as we orbit around the sun. So then it's a question of, can we actually find the physics that we're looking for? Even if we know for sure that it's there, would we be able to find it? This is the question that I'm trying to answer. So the problem that I've been stuck on for 5 months is that when asking this question, we were getting weird results. So what you expect here is to get a number, and the number tells you how likely it is that you measure this. And we were getting a number that was 1,000 times bigger than what it should have been. So that basically was telling us, like, not only will you recover it, but you will have a detection of everything and, you'll do amazing stuff. It was not realistic. And it has taken us 5 months to figure out where this factor 1,000 was coming from. And of course, it's just, at the end of the day, it's just some coding thing, something that needed rewriting. but this has been bugging us since April, since the end of April. Yeah, it looks like we solved it. So there's still, now we've moved on to the next bug, but at least this one is solved. It's something that I was like banging my head against the wall for about 4 or 5 months. It's just a week ago now that we solved it. So yeah, or like Monday, I did the test that confirmed that we probably solved it. So if anyone follows me on Mastodon, I put out a post saying, really happy might have solved this. So thanks for the question there, Dave, because it gives me a chance to speak a bit about my current ongoing project. But yeah, at the end of the day, these things are usually just bugs and numerical bugs. So it always takes a while to iron this out and get it working. But once it works, it's great. And once you fix the bug, it's a great feeling. Strange question, a lot of quotes. Okay, that's a time travel one. So I thought it was connected, so I'll come back to that in a minute. Okay, so let's go through the comments from the beginning again. I think every time it is shown, Deanna sneakily changes 1 pixel in the CMB to see if we notice. Yeah, maybe it's an experiment, and every time you see the CMB, it is very, 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 very slightly different. And seeing how long it takes you to notice. Of course, people who know me well know that I would never do that to the CMB. However, it would be a fun thing to do sometimes, just to see how, like, just write a hidden message in the CMB and see who catches it. Getting some fun ideas for some hidden Easter eggs in the CMB moving forward. If I have time, which is not something I have an abundance of these days, but next time I have time, maybe I sneak some Easter eggs into my slide deck for anybody who's coming in regularly. Okay, so back through the questions. I mentioned on Mastodon that I had a bug. Potentially solved it. Very happy about that. Thank you for asking me that. Question about orbits. We'll go to inbox. We said that. Okay. Any opinion on anti-hydrogen or antimatter in general being affected by gravity normally as opposed to being repelled? This is a really cool question. So thank you for that question, Ben. So there was a headline on the news a few days, weeks, at some point in the last 2 weeks. I think it was last week, not this week, last week. There was a headline at some point that was slightly misleading. And the headline was along the lines of scientists get closer to understanding the mystery that is antimatter. Yeah, no. That was a bit of an over-exaggeration of what actually happened. So we expect that antimatter is affected by gravity in the same way that normal matter is. There's no reason why it shouldn't be. Based on what we know, so antimatter is like matter's evil twin. For every matter particle, you could hypothetically have an antimatter particle. For an example, if you have an electron, you could have an anti-electron. It has opposite charge and opposite spin, and if they meet, they annihilate and produce photons or radiation particles of light. In the very, very early universe, there was a lot of matter and a lot of antimatter, but a hint more matter than antimatter. As the universe cooled down, matter and antimatter met, they annihilated, they produced photons, particles of light, and there was a small amount of matter left over at the end. Fun fact, these photons that were produced by matter and antimatter annihilating in the early universe are the same ones that today make up the cosmic microwave background radiation. So these photons, most of them were produced by matter and antimatter annihilating in the early universe. It's the bath of photons in the universe. So we've got 3 CMBs and we're not even 15 minutes in. It's going to be a CMB heavy day today. So antimatter behaves a lot like matter, except it has opposite quantum numbers, as we like to call it. And when matter and antimatter meet, they annihilate. So based on what we know of antimatter, it should fulfill the same gravitational law that normal matter does. The reason being, when we talk about antimatter, we talk about swapped quantum numbers, but we don't have a quantum number that defines how something interacts with gravity, because to do that, we would need a theory of quantum gravity. So we've always suspected that antimatter would behave the same as matter in terms of gravity. However, this is something that is very, very, very difficult to test, because antimatter is highly unstable. As soon as it meets matter, it annihilates. So trying to do experiments where you have antimatter and you can see how it's affected by gravity is very difficult to do. But scientists were able, maybe antimatter is good one and normal matter is the evil twin. Yes, maybe that would make sense. I mean, or they're just like each other, both think the other one is the evil twin, right? That's probably how it works. So yeah, it's very difficult to confirm if antimatter is affected by gravity in the same way that matter is. But a couple of weeks or 10 days ago, or at some point in the last 2 weeks, time is a blur right now. At some point recently, there was the announcement that science is closer to unveiling the secrets of antimatter. Scientists produce a lot of antimatter, and were finally able to confirm that antimatter does indeed behave the same way as normal matter in the presence of a gravitational field. So a more correct headline would have been something along the lines of scientists confirm expected result, which of course is, it's important. It's how science works, but it's not as clickbaity and it's not as attention catching. Scientists baffled by antimatter. They like doing that. Every villain is the hero of their own story. Very, very true. And yes, some heroes are the villain of their own story too. I'm sure that goes both ways. So yeah, it's a great question. On my opinion, as you did ask for my opinion personally, so my opinion on antimatter being affected by gravity is good. We expected this. We confirmed it. That's great. It's very good when we confirm our hypothesis, because then we know that we're on the right track. It's also very fun when you find something that you didn't expect, because then you need to throw out physics and redo some stuff. So that's also fun. So my opinion is good stuff. My opinion was also the headlines were overhyped and a bit exaggerated and didn't need to be so dramatic, but they were what they were, and it got people talking about antimatter, which is always fun. But yes, antimatter behaves the same way as normal matter does in a gravitational field. This is great. This is what we expected. But yeah, this is cool, and it's great that they're now at the stage where they can produce enough antimatter to actually test this. So it's still very interesting, and it was nice to read the stories and the paper behind it. But as always, bear in mind that a lot of science news headlines are sensationalized. I never really understand why, because science is amazing and cool and mysterious, and it's so fun anyway. We don't need clickbaity titles. I am working on invisible ways, producing the first fraction of a second of the universe. This is like something out of a sci-fi film. We don't need to hype it up and make sensationalized headlines. There's no need to. It's already pretty damn cool and amazing as it is. We don't need to add this fluff around it. But unfortunately, that's how it's often portrayed in the media. I guess headlines of like slow and steady progress towards confirming our hypothesis is not as catchy. A scientist no longer as baffled by antimatter in the universe. But yes, it's a very cool topic, and it's a good question to ask because it was in the news, and I am always happy that you will ask me questions about stuff happening in the news. Okay, back through the questions. I know we had a bunch of questions at the beginning. Okay, so we did the antimatter one. We did the comment about dark matter is not interacting. It's the normal stuff. So yeah, why does normal matter interact? Random thought you had sitting on the bus this week. Great. I love those random thoughts. Could primordial black holes explain the antimatter imbalance due to Hawking radiation? This is a brilliant question, David. This is really, really excellent question. So, could primordial black holes explain the matter-antimatter imbalance due to Hawking radiation? I love this question. And I have a paper on this, which is one of the reasons I love this question. So, primordial black holes are black holes that are formed in the early universe. They are a hypothetical type of black hole. When we think of black holes, we usually think of stars that have reached the end of their lifetime. A star is a constant battle between gravity pulling things inwards, pressure going outwards. When a star reaches the end of its lifetime, eventually gravity wins. The star will explode as a supernova, and the core will collapse into a black hole. Then you have a black hole, which is a region of space-time that is so dense that nothing, not even light, can escape. You'd need to travel faster than light in a vacuum to escape a black hole. As far as we know, nothing can travel faster than light in a vacuum, and therefore nothing can escape a black hole. These are the stellar mass black holes, or the supermassive black holes. These are the ones that at some point were a star. But you can have another type of black hole, which is a primordial black hole. A primordial black hole would be created in the very, very early universe, where you have a region of space-time that is so dense that it can directly collapse to form a black hole. So you don't need to go through the whole stellar evolution and things like that. So you just get a region of space-time. It's really, really dense, and it can collapse to form a black hole. These primordial black holes are predicted in many inflationary models, like this expansion rate in the early universe, this exponential expansion period of exponential expansion. So primordial black holes have a strong theoretical motivation, and they're also really interesting because they could account for some or all of the dark matter, depending who you ask. Seems like there's a paper every week, there has been for the last few years, about this. Depending on your assumptions of primordial black holes, they may or may not be the dark matter. But hey, Savan, great to see you as always. Nice to have you here as well. I've seen a couple more questions, and I'm going to go through this one of primordial black holes and get to the rest because this is a very cool question. So there's a process that we think black holes do, which is Hawking evaporation. And the idea of Hawking evaporation is two particles created from the vacuum of the universe, a particle and an antiparticle. This is something that happens pretty much constantly in the universe. The universe is full of this vacuum energy. This vacuum energy can be used to produce two particles, particle and antiparticle, which pop into existence, immediately annihilate, and go back and kind of return the energy that was invested in their creation. This is happening constantly throughout the universe. So then the question is, what happens if this pair production takes place very, very, very close, or even on the event horizon of a black hole? Now, if you have a pair production, a particle and antiparticle pair on the event horizon of a black hole, what can happen is one falls in and the other goes out. So they're produced, and instead of immediately annihilating, they're flung in different directions. One is pulled into the black hole, one is pushed away. So at this point, you've kind of created a particle from nothing. So to compensate this, the black hole loses mass because then it has to return the energy that was kind of borrowed from the vacuum of space. So you pair produce particles on the event horizon, one falls in, one goes out, the black hole loses a bit of mass. Over time, the black holes would eventually evaporate. And this is a very, very cool process. What happens to a black hole when it evaporates? We don't know. Would probably produce a huge burst of gamma ray energy, which is how we're hoping to find this type of event, but we're not really sure. But the idea is black holes could have Hawking evaporation, by which they pair produce particles. Okay, so next question. Can black holes, so what particles are produced when we have this Hawking evaporation? And the answer to that is basically anything can be produced. You can produce normal particles, you can produce antimatter, you can even produce dark matter. So I did a project when I was in Brussels with the people in Brussels that focused on the question of, if you have primordial black holes that have undergone Hawking evaporation throughout the history of the universe, could these produce the dark matter that we see today? And the cool thing is, if the dark matter is produced in these primordial black holes via Hawking evaporation, it is slightly faster than normal cold dark matter, and therefore it prevents galaxies from forming as efficiently. So what we did is we looked at the overall distribution, like how matter is distributed in the universe, and we used that to put limits on how much of the dark matter could have been produced by primordial black holes. But another question we ask is, if you're producing particles in primordial black holes, can you actually produce particles and antiparticles? And would you be able to explain the asymmetry between these two? Would you actually be able to explain these? And the answer is it's complicated, but I just want to point out that the question you asked here, David Howden, is exactly the question we were asking in this paper. So it's a very, very good question. At least we thought it was worth it was writing a paper about. So if you produce particles of normal matter and antiparticles in an evaporating primordial black hole, then you could actually produce an imbalance. You could produce more matter than antimatter. So that's pretty cool. But what we found in this paper is that you can't do both of these things. So you can't produce enough dark matter to be a substantial contribution today and at the same time solve the matter-antimatter imbalance. So there's a very small region of possible parameter combinations that you could say, okay, if all of these conditions are fulfilled, we could explain matter-antimatter imbalance with evaporating primordial black holes. But you can't then simultaneously explain dark matter, so one or the other. So it's a very good question. The overall answer, I would say, is that it doesn't seem like the most likely scenario, because you'd have to do a lot of fine-tuning of your model. Like, you need the primordial black holes to have a specific mass, you need the evaporation rate to have a specific value, you need it to evaporate into specific particles over a specific time phase. So So the overall conclusion was it's probably not the origin of matter-antimatter symmetry, but it is a very interesting possibility, and you could have that in combination with something else. So that question is like you're thinking like for a physicist, because that is exactly the type of question we asked and put in this research paper. And it was very cool for me to think about this weird model where you have primordial black holes, which we're not even sure if they exist, evaporating via Hawking radiation, which is another big question, and then producing the dark matter. And the fact that we can even ask this question and find cosmological observables to answer this question is really cool. The fact that we can look at how galaxies look and say, like, there's too many galaxies for dark matter to have been created in primordial black holes. That's ridiculous. And this is what I mean, that our research is already science fiction enough. We don't need to embellish it. It's already pretty cool. But that is a very, very cool question. And I thank you for that question as well, because based on your two questions, I've now been able to talk about two of my research projects. And it's always fun to talk about my own research projects. So yeah, that was a very good question. I thought I read that Hawking radiation would be very slow for bigger black holes and increases to very rapid for small ones. That is very true, but wouldn't a bigger black hole go faster because of the surface area? So you have two factors that play a role here. You have the surface area and the mass. And the mass of the black hole actually plays a bigger role in the rate of evaporation, of Hawking evaporation. So very, very small black holes, you basically are interested in the ratio between the surface and the mass. With very, very small black holes, you could have very fast evaporation. With very big black holes, it's a lot slower because there's just more mass to get rid of. Like a supermassive black hole, we're talking about billions of times the mass of the sun. It's going to take you a while to get rid of that mass. One cool thing about about primordial black holes is, depending on the mass that they have when they're created, they could actually be evaporating on timescales of like today, basically, or within the next few million years, plus or minus. So then we can look for things like gamma ray bursts to see if gamma ray bursts, which are big bursts of gamma ray energy, they're not going to turn you into the Hulk. Don't worry, just generally don't go near them because radiation is dangerous for you. So these gamma ray bursts could be a sign of primordial black holes. Unfortunately, based on the way we've seen them behave, it doesn't seem like we've been able to actually see any Hawking evaporation from primordial black holes yet. There's a delay in the mute button. I just tried to mute myself to cough and it muted like halfway through. My throat is a bit raspy again, just in overall tiredness. Is that equivalent to thinking of the ratio between the surface area and the volume? Probably. I would need to recheck the formula because I can't actually remember off the top of my head how the formula for Hawking evaporation goes, and I should because we wrote it down enough times. But I do think the mass plays a much more dominant role. So is it equivalent to thinking of mass as surface area in the volume? So the mass of a primordial black hole is not, or of a black hole in general, is not directly proportional to the volume, because of the fun way with how the Schwarzschild radius behaves, the event horizon behaves. So it's not directly equivalent of thinking about the ratio between the surface area and the volume, but it's a good approximation. Okay, going back through the questions. And hoping that the tea will make me cough less. I think it's just because I was talking a lot last week. I gave a seminar again 3 days ago, and I'm still tired from that. Okay, back through the comments. We just did the primordial black hole matter antimatter. Excellent question. We discussed the CMB and me hiding stuff in the CMB. Okay, so we had a strange question from James, or at least James raised it, a strange question. If time travel is maybe possible, shouldn't that mean that all time and possible time scenarios are recorded somewhere? Shouldn't that info be detectable? This is a very interesting question. So if time travel is possible, does that mean that the future is already written? Does that mean that everything that can happen in the universe is written somewhere? This is a good question, and we can get very philosophical with this, right? Because if time travel is possible and you were able to travel into the future, is that a fixed event, or is that something that you can alter? In the same way as if you travel into the past, can you alter the course of events? And this is something that has been covered in countless sci-fi shows. And the thing is, because time travel basically breaks our laws of physics as we know it. We have this idea that time moves forward. It's an arrow of time. It moves in one direction. The other three dimensions that we have are up, down, left, right, in, out. You can go in either way. You can go back and forward. But time moves in one direction. There is one arrow of time. And therefore, jumping around in this is not possible. You have cause and effect. You can't change this. You can't alter the order of things based on what we've understood of physics so far. So asking to give a scientific answer of what would happen if we were to be able to time travel, we really don't know, because first of all, it's like, how would you even time travel? What does that mean? Does it actually mean that things are already fixed, that everything that is going to happen is already set in course? Does that mean there's no randomness in the universe, or is everything predetermined? I don't know the answers to these questions, because once we throw in time travel, there's not an equation I can point to say, like, this is what's going to happen, right? So time travel into the future, at least, would break. So you could argue we're always traveling through time at the rate of 1 second per second, right? Which is not an actual satisfying answer. So if time travel were possible, it would break what we think we know about space-time, and therefore we don't have a rule book. We don't have guides that I can point to and say, like, based on our understanding of physics, this is what would happen, because we've just thrown out the manual. There isn't one when we put time travel in there, which is why it's so cool to play about with in science fiction, because you can do a lot with it. You can ask these questions of, are there fixed points in time, like in Doctor Who, events that can never be modified? Is everything in constant flux? Can you modify the past like they do in 12 Monkeys, or does that change the course of events? I think it's a really fun question to consider, but if that information is recorded anywhere, why would it be recorded? If we have time travel, you record. So let's say we have time travel, every possible scenario is written down somewhere. Where would it be encoded in some type of information in the universe? I'm not sure. I think it's a very fun thing to wonder about, but it's not something that we can really answer from a purely scientific perspective, because once you turn on time travel, the laws of physics get weird. I think you could argue, like, seeing into the past is always possible. That's what we do when we do cosmology. We look at faraway objects, which means we're looking back into the past. And that is something that we do know how to do. We do know how to look into the past. But then how do you look into the future? And so comment here, the future is in superposition of all outcomes, but it only collapses to one when we travel to it. So again, this is a possibility, right? That in the same way that you have a quantum wave where every possible path is encoded, every possible outcome is encoded, and once an observation happens, you collapse the wave function and you determine the outcome. So could you have something like that, where every future event is encoded in some waveform with a different probability, and only when we travel there do we collapse it? But then you could say, like, if we invent time travel at any point in our future, at any point humans invent time travel, that means that they will travel to these future events. So then all of these waveforms would already have collapsed, right? So then we go back to the same thing of, are they really in a superposition of waves if time travel is possible? Or do we already collapse them by the fact of being here and inventing time travel? Again, this is something that we're moving outside of the realm of what can be discussed with physics, because once you turn on time travel, especially into the future, you break things, you break physics. Time travel into the past would also have problems with cause and effect. If you can go back and change the cause, do you change the effects? But then if the effects change, how would you know to go back and change the cause? You enter paradoxes. It's really fun to think about, and it's something that sci-fi a lot of sci-fi media explores in many different forms, because it's such a cool topic. But it's just very difficult to answer from like pulling out equations and manuals and guidelines, because they break down. I have not seen Tenet. It is on my list of sci-fi films to watch, but that's a very long list. I actually think, so there's a lot of sci-fi shows that do time travel in different ways. Doctor Who's one of my favorites, just because it's a show at its core about hope and optimism, and humanity being its best. So I think that one's very cool. But I do think one of my favorite ones in terms of the rules of time travel is actually 12 Monkeys, the TV show. The film was okay. It was a lot of, usual stuff. But the way they portray the laws of time travel in 12 Monkeys, I was really impressed with it. And if you haven't seen it, I recommend it. It's 4 seasons. It is entirely bingeable, although it does feel a bit more catastrophic now because the premise is there's a virus losing the population. When it came out, it was great. And then you watch it again after 2020, you're like, oh, okay. Suddenly hits a bit closer to home. So I think as long as sci-fi shows are consistent with the rules they set up for time travel, it's fine. And I know I've gone on a tangent here. But I'm also okay with sci-fi shows using time travel because we don't have the answers. What annoys me is when sci-fi shows use things that we do have the answers to and then try to do sci-fi on top of that. It's like, no, this is solved. This is not the fiction part. This is the science part. As an example, is the show Another Life. Was it called Afterlife? It's a terrible show. But the thing that annoyed me the most was when they had flashes of light going past their spacecraft and they said that's accelerated dark matter. And I was like, literally the one thing we know about dark matter. Call it something else. Call it a tachyon. Just don't call it dark matter. Rant aside. Coming back to the question, time travel is a very fun thing. I don't think we can actually answer what would happen from a scientific perspective if this information is encoded anywhere. If there is a universal waveform with every possible future scenario encoded there. We can't answer this because once you throw in time travel, you throw out physics. So you can either have time travel or you can have physics as we understand it today. Of course, we might be completely wrong and we might find time travel and then figure, right, okay, now we figure out laws of physics again. Yeah, like dark matter being a magical substance. No. We know what dark matter does and doesn't do to some degree. Doctor Who is great. I love Doctor Who. Reversing the polarity of the neutron flow. This makes zero sense. Don't use scientific words. Just invent words. They do this to explain the TARDIS. They have the Eye of Harmony. Okay, fine. I don't know what that is. I don't need to know. But when you talk about neutrons and polarity, these are science words that have meaning. Okay, rants mostly closed for now. My conclusion is time travel is fun and a great thing to throw into sci-fi shows, but very difficult to throw into a physics equation. But it would be really cool if we could time travel sometime. It's like the question, if you could do like one trip in a time machine, knowing that you're not going to affect anything, just to go and experience a different time, what time would you travel to? It's a really interesting question. And I love people's answers about that. Surely we have time travel into the future, but only at a fixed speed of 1 second per second. Yes, we are constantly traveling into the future at a speed of 1 second per second, which personally I don't find a satisfying answer in terms of time travel, but you're not wrong. Okay, back, where were we? Up here somewhere. I've taken quite a while to answer questions, so now I have to scroll quite a way back to find the questions where I left off. Strange question was a very fun question. We did antimatter. Did you see Tom Scott's documentary about the VLT and the ELT? I did not. I'm guessing that is the very large telescope and the extremely large telescope because we are exceptionally good at naming things. These are ground-based telescopes, as the name implies. One is going to be big, the other is going to be exceptionally big. I did not see the latest documentary about it, so not sure. Comment from James here. Confuse yourself. If matter and antimatter act the same, what differentiates the two? How do we know which is which? So they act the same in a gravitational field. That was what the new results found, that in the presence of gravity, they both fall down. But they have different quantum properties. So for an example, the antiparticle of an electron is a positron. An electron has negative charge, a positron has positive charge. So based on that, within the standard model of particle physics, we know what charge and spin things should have. So that if they have the opposite, then you say, great, that's antimatter. So it's not that they behave exactly the same. This new study found that their response to a gravitational field is the same. So if you put them in gravity, they both fall down. That is good. That is what we'd expect something to do. The day something falls up, unless you're in a weird gravitational field, then you have some questions. So yeah, the conclusion there was that matter and antimatter are both attracted by the gravitational force, but their quantum numbers are flipped, and so one is positively charged, one is negative, one is like up, one is down in terms of spin. Not that spin is actually an up and down. So yeah, they don't behave the same in every regard. They just behave the same in terms of how they respond to gravity. Comment here from Scott. I'm not sure what it's referring to by now because I'm like 20 minutes late with the comments, but it reminds you of a professor at a picket sign, like, what do we want? Gradual change. When do we want it? After peer review? Yes. But that's not, I guess it was about dramatic, catchy headlines. That wouldn't be dramatic and catchy, would it? So instead, we have fancy things, fancy headlines. Okay, we had to write an essay on that as kids. Depressingly large number of my fellow kids wanted to go back and watch a football match. Really? Huh. That's I mean, I get it as kids that that might be the most interesting thing. You know, one thing that I would love to see if there is the Live Aid concert, but that wouldn't, if I had like 5 trips, maybe I would save one for the Live Aid concert, but otherwise it wouldn't be my top choice. I would, I think there's so many different possibilities there of like what would, where would you go? I would go back to a week last Tuesday, as they do in Red Dwarf. Yes. Yeah, it's just very curious. Like, you get one time travel trip and a return journey. You're not going to be stranded there, just to go and see things, past or future. Where would you go? And I think for me it changes a lot, because if it's past, then I would definitely go to the past. But if it's past or future, I would absolutely go to the future. But then what would you do with the knowledge that you gain? Like, if you go to the future and see that humanity has wiped itself out and that that is inevitable, how do you live with that knowledge? Of course, we could try to fix that now by actually not ignoring the climate crisis. But again, a tangent. So yeah, it is very interesting to think, like, where would you go if you could time travel? If you could time travel anywhere, where would you travel to? So another question that from some time ago: if a black hole whose singularity is pure matter merges with a black hole whose singularity is the first exact antimatter clone, would you get a Kugel blitz or white hole or annihilation into nothingness? So I'm not sure what you mean about the singularity being either matter or antimatter, because the singularity of a black hole can mean either two things. It can mean the event horizon of the black hole, which is more of a numerical singularity than an actual singularity. Or do you mean the singularity like the center of the black hole? So in either case, we really don't know what happens beyond the event horizon of a black hole. So we don't know if black holes are made with matter or antimatter, probably maybe a mix of both. So having a black hole and a kind of anti-black hole meet and annihilate, what would happen? I mean, it would probably be pretty dramatic, but it's quite hard to consider, because we don't know if what a black hole is made of, because once you go past the event horizon, you don't know what's inside. And it's quite likely that you have matter and antimatter. Of course, these might annihilate, but then they would never even escape the black hole, so it doesn't really matter. But we don't know what is inside a black hole. So it's quite hard to imagine a black hole made of antimatter and a black hole made of matter, and these two meeting and annihilating. So it is, because then you'd need to ask the question, like, how do you form a black hole of antimatter in the first place? Because even if you have this region of space-time that collapses and forms a black hole, then it's going to accrete everything into it, and there's just much more matter in the universe for it to accrete. Unless you want to go down the path of maybe the reason that there's, just like random idea I'm throwing out here, maybe the reason that there's more matter than antimatter is because the antimatter is tied up in primordial black holes. But then we'd need to understand why antimatter fell into primordial black holes, but matter didn't. Because as the recent experiment just showed, they behave the same in the presence of gravity. So I think it would be quite hard. So beyond the fact that we don't know what black holes are made of, I think it would be quite hard to envision a black hole made of antimatter, purely of antimatter, that could then annihilate with a normal black hole. But that is also a cool question. If you're going to the past, can you bring antibiotics? Yeah, so I think I would add the rule here that you do this journey unharmed, right? You're just an observer who gets, maybe not even journey, you just get to open up a TV screen and watch some event, either in the past or in the future, in the entire course of the universe. Doesn't have to be humanity related. You can watch one event, either past or future. You are not in any way impacted by this. So yeah, rather than traveling there, you just get to witness it. You can add in if you want that it's like fully immersive experience, so it's like you're there, but maybe it's a virtual reality type thing where it doesn't do you any harm and you don't harm any others. So you don't need to bring antibiotics, or just bring your snacks. Plot twist, you actually cause the end of humanity by trying to prevent it. Yes, well, that's Umbrella Academy for you. I go back 10 years to stop past me from smoking. I mean, I get that, but the rules of engagement here are that you can't change anything. You can, because otherwise you go back and fix a mistake in your own life. But you can. There was some random post I saw on some social media recently, of like if you want to go back 10 years ago and prevent yourself from making mistakes or change something, whatever. What would a version of you 10 years from now want to change about your current self, and what's stopping you from changing that? Imagine you're a time traveler from the future and you just found yourself. What would you change about yourself? I thought it was a very interesting, one of those like deep and mysterious posts, and I think it was on Mastodon or something like that. I was just like, okay, yeah, I'll think of myself as a time traveler from the future, fixing my own mistakes now. It's an interesting philosophy. Since black holes move like any other object, do they do things like slingshot with each other instead of always spiraling into collide? What if their event horizons graze instead of direct collision? Excellent questions. So, I know we're having like 3 conversations in parallel here, and there are still questions I haven't got to. I will carry on going through them in a minute. So, black holes move like any other object. Do they do things like slingshot with each other? Yes. You can have black holes slingshotting each other. If they come close, they can push each other out. A black hole is just a region of space-time that is really, really dense. They behave the same way as a lot of other objects do, in the same way that you can have stars that come close by and then move on. You can also do that with galaxies that come close to crashing and then slingshot away from each other. You can have slingshot things with black holes as well. So they don't necessarily, it very much depends on the angle at which they approach each other. Okay, so let's just imagine one is static, just because it's easier, and you have another one approaching kind of at a grazing angle at high velocity. It might not get caught up. If it's moving slow enough, then it might get caught up by this one, and then they start spiraling around each other. So you absolutely can have slingshots and black holes being ejected. Then there's the fun idea of rogue black holes, which are black holes that have been spat out from their own galaxy by some random event like this, and now they're traveling freely in the universe, not bound to anything, just like a black hole somewhere in the universe. You imagine you set up your spaceship, you travel to another galaxy, and suddenly there's a bloody black hole there in front of you. Would be a bit chaotic, but there is this idea of rogue black holes traveling throughout the universe. Question number 2, in the same question here by Paul. What if their event horizons graze instead of a direct collision? So once the event horizon is the point of no return. It is like the outermost layer of a black hole, so to speak. But once you get to the point of their event horizons touching, they've already started the in-spiral phase. So in the same way, if you have stars that slingshot around each other, they're not really going to graze. If they're close enough to graze each other, they would be close enough to start orbiting around and actually do the full in-spiral. So I don't think you'd have ones that are close enough to graze each other, but not attract each other completely. Because once you're that close, you would just merge, basically. But then you get fun things of like what happens to the event horizon of 2 merging black holes. And there was a lot of simulations done on that, and depending how it happens, you end up with like a ring over an event horizon instead of a sphere, which is very cool. And then you have this ring black hole, which is referred to as like a naked singularity, and that's weird. But that's something that can happen. But yeah, you can have black holes slingshotting around each other and doing the Roadrunner and Coyote move around each other. Very scientific, technical terms there. Armageddon reference for anybody. That is such a terrible film, but it's such a fun film to watch. So yeah, you can black holes slingshotting around, but I think if they got close enough to graze past each other or to graze each other's event horizon, they would coalesce and start spiraling into one black hole. Don't know why there's an explosion there. There's no explosion involved, unless you have a neutron star involved, and then you do get a. But no, they just kind of go boom, boom, and collide. There's no dramatic explosion involved there. Of course, if you can view any event in the past, you can use it quite voyeuristically to spy on your neighbors. Yeah, but like you only get one chance at this, right? I'm not offering you unlimited views into the past. It's literally one. Would you waste that on spying on your neighbors? I know, but do you want to see the creation of the earth, the destruction of the earth in the future, the creation of the pillars of creation, maybe? Would you want to witness a cosmic event or a historical event or which or both? So yeah, it's a fun question. I don't actually have a clear answer as to what I would do if I was offered this like one snapshot. I think it would be really cool to see the point at which humanity leaves the point of first contact, the point where humans first encounter a civilization in the future. But then there might be the thing that there's nothing to show because this event never happens, and that would be a huge disappointment. But I don't have an answer either. It's just something that I think is fun to think about. Okay, let's go back to the questions because there were some that I overlooked earlier. Let's see. We covered that one. We covered the matter antimatter black holes. Okay, we covered Hawking radiation. I think yes, we covered that one because of the surface area. Okay, we covered that one. The future is a superposition. We covered that one. Okay, I think I might be up to date with all of the comments now, except maybe one. Let me just check again. We have time travel into the future. We covered that one. Red dwarf comment, football matches. We covered these. Lots of really fun comments so far. It's always fun when we go off on random tangents. Okay. So yes, I think we're pretty much up to date, except the 3 new ones that just appeared. Is it possible to have a binary planet system orbiting a star? Have any been observed? Yes and yes. So, right, a binary planet system orbiting a star. Okay, I read that initially as a planet orbiting a binary star. So you want a binary planet system orbiting a star? Well, I think it is highly possible, but then it very much depends on your definition of a planet, right? Because based on our definition of a planet, a binary planet would not actually count as a planet because it hasn't cleared its own orbit. So part of our definition of a planet is that it has cleared its own orbit. So there's no other big space junk or space objects around it that are of similar size, which is why Pluto got demoted as a planet, right? But we know that Pluto has its moon, Charon, and they're quite similar in sizes. And these are orbiting each other as they orbit around the sun. In a sense, the moon and the Earth are orbiting around each other as we travel around the sun. So then it very much depends what you define as a planet. So do you want a binary planet system? I think just based on our definition of planet, this doesn't fit in with it, but there's no reason why it couldn't exist based on what we've seen from Pluto and Charon. So you can have a 2-body system that is locked in its own orbit and then around the star as well. But based on our definition of a planet, that's not something that we would have. But so have any been observed? Other than the Pluto Charon example, you could think of anyone with a moon, and then it really depends, like how do you define a planet, how do you define a moon? Yeah, it's got to be going back to see what a man named Jesus was. That would answer a lot of questions, and I guess from a historical perspective and a cultural perspective, that would be a really interesting one as well. What about a multi-planetary cluster? So you want a cluster of planets that is orbiting around the star? Again, we have the problem here of how we define planets. But yes, physically it would be possible, but it really does come down to how we define things. Okay, I don't think the Earth has cleared its own orbit. There's this big moon thing. Perhaps we'll be kicked out of the Planet Club and have to hang out with resentful Pluto. Yeah, so I think I can't remember exactly what the 3 criteria are, but it doesn't really count moon. So it's like anything else orbiting around the system. I can't remember the exact definition, but like moons are considered the mass difference is big enough that it's considered its own moon and it's kind of tied to the planet. It's not a different thing, different object. But yeah, I feel like it's quite a fuzzy area there of how we draw the line between planets and moons. But it very much there is like a scientific standard. I just can't remember the 3 rules. Okay, sci-fi plot twist. You trade places with him. You end up living his life and he comes back here and has to deal with modern misconceptions. If someone wants to write that story, it could be really fun to read. The Castor system has two pairs of stars that each orbit their partner. The pairs orbit each other, and the third pair of stars orbiting outside it all. Yeah, so you can have binary stars. We have seen binary stars that exist with planets orbiting around the binary star. But then it gets really messy, right? Then you have the three body problem. You have too many objects in motion, and it just gets really messy and hard to just find. So it's fun. It's fun. Part of it had to do with the very center of the planet and the moon being inside the planet at all times. Yes, exactly. Something like that. So the moon is orbiting around the Earth, and the kind of center of gravity between these two is within the Earth. Now, if you want two separate planets, then the center of gravity would be somewhere in between them, unless you have a big planet, a big size difference, and then one is basically going to be a moon. But yes, that is one of the three rules that I always seem to forget. Okay, so I do believe I have caught up with all of the questions except one that I noticed and ignored earlier. There was the question at some point by David Dunn of how are you doing? Thank you for that question. It's always nice when people ask that. I am doing mostly okay. Honestly, I'm a bit overwhelmed with work right now. I'm writing a grants proposal that is due in 2 weeks, and it's taking up a lot of time and effort and energy. And I have been traveling way too much over the last few weeks, and I've given a bunch of talks. So overall, I feel like my energy is quite low right now. And it's one of those times in science where, there are good days, there are bad days. There are times where we have to push more and times where we can let off slightly. And currently, I'm at one of the times where I have to push more. And it's just a bit draining, but I will then take time off to compensate because I think it is important to not push all. You can't work at 100% all the time, right? Sometimes you can push, but then you have to take a step back and chill. And I've just been pushing for quite a while now. But in 2 weeks, I hand in the grants. Then I go on another trip and another conference and another talk, and then I can rest. So, in answer to the question of how am I doing, tired, slightly overwhelmed, and a bit stressed in general, but still with a positive outlook about things, I would say. I didn't have a positive outlook a few days ago where I got very overwhelmed by things, but currently I once again have a positive outlook about research and the fact that, as I mentioned earlier in the stream, I solved a problem we've been battling with for a few months. That definitely adds to the pile of good things over the last few weeks. So, yes, to answer your question, I am mostly okay, just a tad tired, but overall doing well. Conference fatigue is real. It really is. And, I love traveling. I really do. But I have been traveling a lot this year. I actually went through and checked, and I have not had more than 4 weeks in between my traveling since February. So between February and now, I have traveled with no more than a 4 week interval at home. So I stay home for 3 or 4 weeks and then I travel again. Now it's like 10 months into this, or 8 months into this, and it's getting a bit much. I did a trip in August, got back like the last week of August, and then the first week of September I traveled again for 2.5 weeks, in which I went to 5 countries, did a conference, a collaboration visit, and a bunch of other things in between. And then I got back and then traveled again for another conference. And I got back literally on Thursday night. And now I have 2 weeks before I travel again. But then I have a whole 7 weeks until my Christmas plans. So yeah, conference fatigue, travel fatigue, and grant writing fatigue has all just come together. I'm in a near constant state of panic with brief respite of severe depression. I mean, that does not sound healthy, but also it does sound like a lot of people I know. You need more coffee and a cafe time. Yes, at least 3 hours per sitting. Cafe time recovers me. I completely agree. I actually also like working in cafes. It's good to get a change of scenery sometimes, and just to go to a random cafe with coffee and enjoy the scenery and take in the difference. If you're always working in the same spot, sometimes it's hard to focus, and it's good to get these random moments working elsewhere. And yeah, basically, because I've been traveling so much, I've been working in random cafes in random countries for the last few weeks. But Yeah, working in cafes is fun, and in the sake of work-life balance and so on, I'm actually taking Friday afternoon on off of work to go chill in the cat cafe with some friends. There's a cat cafe in Helsinki. Last time I was there, they had 8 cats and one bunny, like a bunny rabbit. It was really cool, and they have amazing vegan cakes. So for anyone who's concerned about me, don't worry. I'm taking Friday afternoon off to go to a cat cafe and watch the cats and hopefully a bunny with some friends. So I agree that time in a cafe is definitely a good thing to recover. And next weekend I'm going hiking as well. So I'm not just working. I'm also fitting in some calm and relaxation time. Or if hiking counts as calm and relaxing. Okay, so we've reached the 1 hour mark. I think I managed to get through all the questions. We had some really cool questions today. I love that I got to talk about my ongoing research with gravitational waves and about my project on primordial black holes evaporating and producing dark matter. It's cool that we were able to talk about that. We didn't talk much about the CMB, but I still showed the CMB 3 or 4 times today. So that's always cool. And, I love conversations about sci-fi and time travel, and only did one rant today, which is less than what I expected to do. Or two, if you count the misleading headlines in news articles. So only 2 rants today. One about sci-fi, one about misleading headlines. Not too bad. You didn't even get me to rant about the Nobel Prize. So, I've already done that rant twice this week. Okay, so Cup of Cosmology should be back online next Sunday, same time as usual. Just a reminder that we're not doing any time changes yet. The clocks go back or forward, or whichever the clocks go back in 3 weeks here and 4 weeks in the US, as always. There is a time zone converter on cupofcosmology.com where you can check what time the next stream is in your own time zone. So you can always go in and check what's happening just in general. If you haven't done so yet, please do subscribe to the YouTube channel, leave a comment, like the video. Feel free to share it with people. It's great to boost engagement. Also, feel free to follow me on Mastodon for any general updates. My username is dchooper91_Cosmo, or if you just search for dchooper91, you'll find my 2 accounts, one for Cosmo, one for personal stuff. You're welcome to follow both. And as I mentioned earlier, if anyone wants to get in touch, send me follow-up questions, you can email me, contact@cupofcosmology.com. I always try to answer within a week or 2. Although that said, there are 3 emails that have been waiting for an answer for a few months, but I will get to them at some point. Okay, this has been great fun, everybody, as always. Thank you for being here. It's always nice to have all of you come back and ask questions. It's great to see where you take the conversation. I always come to these things like, let's see where we head today. And it's always fun and random directions that I did not predict. So it's always really, really fun. So thank you, everyone, for joining. Cup of Cosmology will be back online Sunday next week, same time as usual. That's 7 p.m. if you're in Europe, 1 p.m. if you're on the east coast of the US, 10 a.m. if you're on the west coast of the US, and I'm not sure about anywhere else, but that's the approximate time zones. I hope to see you all again next week. And I hope in the meantime, you all stay safe and take care of each other.